we found out that after a long computation, well, it wasn't that long. It was just a single Blackboard. We found that the interesting objects we want to consider are operators that do the following. Remember, we defined these rescale operators so that they would satisfy a relation of this form. And we said that we wanted to think about this as a product in some vector space, thus defining an algebra for us based on this vector space, which is defined over the reals. Okay? And we asked what kind of algebra this was, thinking about this as an abstract product where all we know is that the product of two elements of two vectors in this vector space can be written as a linear combination with real coefficients of elements in the vector space, and thus is an element in the same vector space. We learned that, or we concluded that the algebra was not commutative, as is obvious from the definition in terms of a commutator. Okay? So remember, we said that this was a commutator. And we're lucky in this case because we have an underlying product, which is not the same product that we have here, right? It's not the product in the algebra. We have an underlying product of these objects as elements that act on another vector space, okay? Which is the product that we have when we multiply these operators to define the commutator. But our job, at least your job, for the rest of the afternoon yesterday, was to define this algebra as an abstract object, something that doesn't rely on the fact that these are operators and there is a commutator and there is an underlying product. Okay? So your job was to find out what are the conditions on these f's so that this is an algebra that would correspond to the same algebra that you get if you had this underlying structure behind. So the next question we asked was, is this algebra associative? And for that, we had to test this condition. And compute this. Okay? So I presume everybody did it, right? Who did it? Okay. Very good. Those who didn't do it, was there a problem or did you try? Maybe I should have started by asking who tried. Yeah, then everybody should say, even if you didn't, you should raise your hand and say, yeah, I tried. I was going to try, but yeah. Okay. So those who did it probably found something interesting, right? You found that the answer to this is the following. So can anyone, who did it? You did it? You want to write what the answer was? Excellent. That's the answer. So the answer is that it's not commutative, it's not associative, but instead we get this funny term there. Okay? So that's the answer. Now you would say, well, this looks a little bit funny. How can we remember this? Well, one way to remember it is the following. If you think about this as something that has an order with A, B, and C, you just write with plus signs all the possible cyclic combinations of this, and that will be exactly this identity. So that's the way most people write it. So you start with this formula, and you keep writing the same formula all over and over again And you simply move the labels cyclically in the t's. So this was A, B, and C. Now this would be A, B, and C here, and A, B, and C. And you can check that this is the same identity if you use the antisymmetry of the product. OK, very good. So the next step was to go back and write the same identity in terms of the f's. OK? Remember, this is a product, so we can just do it in terms of the f's. So I presume that the people who found the identity in terms of the f's is a subset of the people who found the answer for this problem. So I'm not going to ask who did it, but I'm just going to say that I encourage you to do it. And the identity that you get for the f's, as I said last time, is an identity that relates two sets, products of two f's. So let's do it for this one, say. We have BC sum E, because this becomes some generator TE. OK? So that's the answer of this product using this formula. And now we have to multiply that with TA. And what do we get? Well, we can pull out these structure constants, because after all, they are just real numbers, and this is a vector space. So we can just factor them out and compute this product. And this product is going to be some F AE with some other label TD D, so that we can put the D here. OK? That's what we're going to get. Now, if you do it for each one of these terms, you will get an identity in terms of the f's. And the identity that you get is something of this form. I'm not going to bother to write the indices. That would be your job. I encourage you to do it today. OK? And this is called the Jacobi identity. Why do they call it the Jacobi identity? Why do people call it an identity? Why do you think?
It's true for any structure constants. So.
Yeah, it's true. Then it's such a silly thing to write, right? It's an identity, so who cares? It's always satisfied.
The identity is independent of the specific framework reference you choose.
Yeah, sure. But the point is that it's an identity if these f's come from a commutator. Okay? But suppose you don't want to talk about operators, commutators. You're a mathematician, and you want to think about something very abstract, right? You don't want to talk about operators that satisfy some other product. You just want to start from here. Okay? Then, in order to define a Lie algebra, you start with any antisymmetric structure constants. Okay? Antisymmetric structure constants. And you make them satisfy what I now would like to call the Jacobi condition. And then you have a Lie algebra. Okay? Of course, if you start already with this, then this is an identity. And of course, the f's that you get from this commutator form a Lie algebra. Okay? But you can start from a very abstract point of view and simply think about this as a product, these things as coming from somewhere else. You just want to test if these things will generate a Lie algebra, and the condition they have to satisfy is the Jacobi condition that you get by plugging this formula in these three terms and checking and writing down all the indices in this formula. OK.
Excuse me?
Yes?
So previously, when I was doing some Lie groups and Lie algebra, some people reference to this top line with T's as exactly this. Is this true, or is this something you can think of as well?
Well, some people say that when you write it in terms of commutators and with the T's, it's definitely an identity, right? As you probably checked when you did this, right? all you were using was that this was a product of something that has the structure of a commutator. There is definitely an identity, right? But I want you to make the distinction and separate that from the abstract point of view, where we can just start with an algebra and impose a Jacobi condition to land on a Lie algebra. Now we have, at this point, we have two possibilities.
Question?
Yes?
Question. Do we use that GAGB is equal minus GBJ or just?
Yeah, sorry, I said, yeah. I should have written it down. So I said that we start with a product that is anti-symmetric. So we want FABC, but I should have written it down. So we need these two conditions. Very good. OK, so at this point, we have two options. One is to put our hats of mathematicians and start from here and develop the whole theory of Lie algebras, classify all of them. After all, they have relevance in physics. So it's a natural question to ask, what are all of them? Can we classify them? And so on. So that would be one path that we could follow. The other path is to keep going using physics and try to find interesting examples and learn how these examples are actually working and what they do for us. Okay? So I chose the second path. And the interesting example is the most basic one, right? Which you can probably guess. So we're going to study a group today, which is a group that you started to study with Anna yesterday. Okay? So today, we're going to concentrate on the Poincaré group. Okay? As a basic group that will lead us to a lot of the physics we know. So we all know that the Poincaré group contains Lorentz transformations and translations. Okay? So if we have our points in space-time, we perform a Poincaré transformation, and we get generally something like this, where this is the translation, and this is the Lorentz transformation. Okay? Now, probably yesterday, you went through this, and you checked that this was indeed a group. So being a group, you found that it has a product structure. It also has an inverse. Okay? But today, we want to study more than that. We want to go into the structure of the Poincaré group and the Poincaré algebra. So the goal is to understand what the Poincaré algebra is. So what would be the first step? Remember what we did yesterday. Well, yesterday we decided to start by representing these objects, which I'm going to denote as lambda, 8. So this would be an element in the group. We decided to represent them as operators acting on a Hilbert space. What kind of operators should they be? Yep, because they contain the identity. So we're going to represent them as operators acting on some Hilbert space. Now, if we want to understand the structure of this group is another Lie group, right? Because it's a group that depends continuously on parameters. And we said that such things are very complicated. What was the trick to understand the group? To understand any of these Lie groups? To study infinitesimal transformation, right? So we want to study infinitesimal transformation. Very good. So an infinitesimal translation is very trivial. We just choose a vector that is very, very small, and that's it. So we can call the infinitesimal translation, sometimes we will denote it by epsilon mu, to remember that this is infinitesimal. Okay, so that would be the translation. But let's try to work out what happens to the Lorentz transformation. So we want to write this as doing nothing, meaning the identity, plus some infinitesimal transformation. And we want to find the conditions on the infinitesimal transformation. Okay? Well, all we have to do is to impose that this is a Lorentz transformation, right? And find out what this object has to satisfy for this to be a Lorentz transformation. So if we want this to be a Lorentz transformation, all we have to check is that it leaves the metric invariant. Which translates into this condition, which you probably did yesterday. Okay? Now, can you start to work out what this is? If you plug this in here, what condition do we get on W?
This metric with the two indices, both contravariant or.
So you did it already? Wow.
I've studied this.
Okay. Well, let's just do it very quickly here. So let's plug it in. So we get eta mu nu, get mu rho plus omega mu rho times. So please check my indices because there is a good chance I'm going to have some trouble if I don't get them right. Okay. So the first part is trivial, of course. This, with the metric, we get eta sigma, rho sigma, which will cancel this. But the interesting part is the next one. So we get omega. With this index, we get it rho here. We lower the index. And the other linear term is omega. We lower the index here, and we get. So what do we get? Oh, OK. So I told you to check my indices. So what am I doing wrong? Why am I in trouble? Yeah, probably it's hard for you to see from here. But what I'm doing now is this term with this term with this term.
Sigma rho with the indices.
Yeah, I forgot to contract with this one. OK? So sigma, I'm contracting with this one, so sigma goes up.
No, sigma goes down.
Sorry. Nu is contracted with this nu, and then sigma goes here. Very good. Now in the next term, what do I get? I get omega
Rho sigma.
rho from the three terms, and then sigma. And this has to be equal to this condition. This is infinitesimal, so I only keep linear terms. Therefore, I conclude that this must be 0. Okay? So that's the condition we wanted to get. Oops. So we find that infinitesimal transformations are controlled by an object with two indices, which is antisymmetric. So how many independent parameters do we have? Number of independent parameters.
And how many dimensions?
Is what?
In 4 dimensions?
In D dimensions. No.
6.
Of course, we're in 4 dimensions. Yeah, very good question. So now I have to learn that I have to be very specific. So we're doing 4-dimensional physics. Oh, I forgot to tell you what my convention is for the. Yeah, this we have specified everything. So I'm going to choose eta to be this metric. Okay. So the number is 4 times 3 over 2, which is the number of independent components in a 4 by 4 antisymmetric matrix, which is 6. And this is called the dimension of the Lorentz group. Or the dimension of the algebra is 6. Okay? Now, if we add translations, translations contribute 4 parameters. And this means that the dimension of Poincaré is 10. Okay? Very good. Now, the translations form a subgroup of the Poincaré group, okay? And this subgroup is what is called an abelian group. What's the meaning of abelian? Very good. That they commute. Okay. So this subgroup is a subgroup where we simply said in our conventions, we always put an identity here, and we have any vectors that we like here. These form a subgroup, which is abelian. There is also, of course, the subgroup of Lorentz transformations, which is a subgroup where we put 0 here and any lambda here. Okay? Now, sometimes the Poincaré group is also called the inhomogeneous Lorentz group. And this subgroup is called the homogeneous Lorentz group. But I'm going to try to use only the terminology that the big one with translations and Lorentz transformations is called Poincaré, and this one is simply the Lorentz group. Okay? Now, what do we want to do? We want to go and look at these infinitesimal transformations as operators in our Hilbert space. So once again, we go to the infinitesimal version. And since this is infinitesimal, we can expand it. Just as we did yesterday. Okay? Where we're going to have operators. These operators are now Hermitian. And you may ask, well, why do I have a minus sign here? And it's just convention. Okay? Or it's convenient. Simply, it's convenient, as we will see. Okay? So these are the generators of the Poincaré algebra. Okay? These are the generators. And now we want to study the structure of these generators. Well, but before we do that, we want to give physical meaning to these generators. Well, the first step is to realize that when we have an abelian subgroup, or we have an abelian group, it's very easy to go from the algebra to the elements of the group. Well, how do we do that? We just know the following. Imagine that you have some element in the group. Okay, so here I'm taking the subgroup of translations. So we have an element in the group. And what if we multiply by another element of the group? What do we get? Well, these are just translations, so we get something that looks like this. Okay? In particular, if we choose B to be A, we just get 2 times the same object. So we can do a little trick here, which is to write any finite transformation, any finite element in the group, we can write it as n times doing a small deformation, a small translation, okay? We just split our big translation into n smaller translations, and we do each of the smaller ones n times. So do you all agree that this is the same? It's just true because it's a billion, so this is completely fine, right? So now we can, the next step in the trick is to take the limit when n goes to infinity, okay? And if you do that, know that this parameter now becomes infinitesimal. So we can use our description in terms of the infinitesimal generators and say that this is okay. Remember, here we don't have any Lorentz transformations. We're only restricting ourselves to the subgroup of translations. Do you know what the answer of this is? If you take the limit, what do you get? Very good. We get an exponential. Okay? So that's the way this object acts on our Hilbert space, okay? Or translations act on the Hilbert space is through this operator. Now, in order to give physical meaning, all we have to do is to say, well, let's see what happens for a vector of the form T0, 0, 0. Let's consider this one. What do we get in that case? Well, we get an operator of the form minus I T P0. And therefore, P0, the P0 component has to be identified with what? With the Hamiltonian of the theory. Okay. Very good. Now, if P0 is a Hamiltonian, what is the 3 vector made out of P1, P2, and P3? Well, these end up being identified with the momentum operators. What else can you recognize from here? Well, you can probably recognize these components of this tensor, okay, the component 2, 3, 3, 1, and 1, 2. These will be identified with the angular momentum. Operators. Okay? Of course, at this moment, I'm just telling you this. But in order to really find out, we should explore more deeply what the structure of these objects is. OK. Any questions up to this point?
Maybe I have a small question.
Yes.
When you identified P0 with Hamiltonian, did you make some implicit assumption about, say, h bar equals 1? Or
About?
But I mean, unit-wise, that would be Hamiltonian has been.
Yes, sure. I'm assuming that h bar is equal to 1. Very good. Okay. So what we're going to do now is something that is usually done for any Lie algebra, in fact. But we're going to do it here in this example, is to find out, we want to find out how J and P behave under a Lorentz transformation. In fact, under a Poincaré transformation. Okay? So how do we do that? Well, imagine that we are computing this quantity where O is some operator and phi and psi are some states in our Hilbert space. Okay? Now, if I want to find out how this operator looks like for our second observer, remember yesterday we had observer 1 and observer 2. We're assuming that this is what observer 1 sees. Now, if we want to find out how this looks like for observer 2, it's not very difficult. Well, we can put an inverse here. Here is a trick. I'm only multiplying by the identity and writing the identity like this, where this U is a transformation, the unitary transformation that takes what observer 1 sees to what observer 2 sees, right? Now here, this is unitary, so I can replace this by a dagger. Once I replace this by a dagger, I can recognize this as being U of phi, and this as being U times psi. And whatever I get here is going to be our new operator, O prime, which ends up being U O U dagger. Okay? So that's what we want to do for J and P under a Lorentz transformation. So we want to compute what this is. We apply some Lorentz transformation, and we want to compute the transformation of this object and see what it is. Likewise, we want to do it for the momentum. And find out what this is. Okay? So how do we do that? Yeah, using that these guys actually occur in an infinitesimal transformation. So the trick would be to start out not with each one of them, but with the infinitesimal transformation that contains them. Okay, so this is what we want to do. If we understand what happens to this, we will be able to understand what happens to them individually, because we just have to compare the coefficient of each of the infinitesimal parameters, right? Well, let me replace this by an inverse. Okay, so I want to do an experiment. I don't know if we have time. Maybe we have. But part of the reason this room was designed in that way, in this funny way that you see, that two levels are at the same point, is actually so that you guys can turn around and work together. Okay? So what I want you to do is maybe to spend 3 minutes, literally 3 minutes, or maybe 4. I want you to tell me what this is, what goes here and what goes here after you compose all these transformations. Okay? Yes? No. Remember, this is under a general Poincaré transformation. This is not infinitesimal. Okay? So I don't want you to use, in fact, that this is infinitesimal. Here, I want you just to compose these operations. So feel free to turn around and talk to your friends. Let's see how this works. I don't know if anybody has actually used a room like that. Have you before?
Yeah, the tutorial.
Oh, in the tutorials. Okay, great.
Yeah. No, I get it.
Yeah.
I know, but it contracts first, and then you, if you can, yeah. So you want to see what happens first, and then you will pivot to. So you always want to try to see the
In the first round, you and
You get a 1.
select the side.
And then once you've done that, then you just write it down.
You gather
And then because there's nothing else, because there's more than there's only 2 variables now, you can't do the rest of it.
Yeah.
Or you can't do the rest of it. So to be able to increase it,
well, translation is just if you make a rotation, then translate, make a rotation. What am I translating? That translates to mean and
Okay, very good. So does anybody have the answer? Not yet? Okay, 1 more minute.
oh, it wouldn't matter anyway because it wouldn't matter and then that's equal to 0 anyway, so it cancels.
Yeah, I think it's just make the just well, if you're saying if you ignore the omega, if you ignore the omega, oh, if you ignore translation.
Oh, I mean, take it as
Well, if you don't rotate it all, you use
Yeah.
So you get right. Well, the rotations are
oh, wait, no.
We can
Okay, anyone? You have it? Do you want to write it on the blackboard there? Yeah, you can write it there. Yeah, that's the purpose of that blackboard. You might wonder why we have blackboards all over.
When you take it to because yeah.
That's almost correct. The Lorentz part is correct. The translation part is missing a piece, right? Does anybody know how to fix it?
Yeah, actually, I realized it is missing a piece.
Oh, you're missing a piece. Yes. Okay. So you have a chance to fix.
Yeah, because I first ordered the missing piece is second order in it. I don't know how much, but it's actually first order. I meant to play this if they're not.
Yes. Very good. Excellent. That's the answer. So that's what goes here. Okay. Okay. So now all I did here was to use the infinitesimal version of the middle part and wrote it explicitly. Okay. So what we want to do is to compare, to expand out everything. This is also infinitesimal. Note that everything here is the identity plus something infinitesimal, and the whole translation is infinitesimal too. Okay? So we can certainly expand out everything and compare terms with respect to omega and epsilon and find what the transformations of J and P are. Okay? So that's an exercise for you. I'm just going to tell you what the answer is. So when we do this one, what we find is something of this form. Okay? And when we do this one, what we find is simply this. Okay? Now note the following. If this was only a Lorentz transformation, meaning A was 0, we wouldn't have this piece here. And therefore, J would transform as a second-rank tensor. Okay? Which is good. Note here, I think careful with the position of the indices. What's the meaning of this lambda with these funny indices in this position? Note that the Lorentz transformation had the indices in a different position, right? Here, somehow one is up and the other, sorry?
The inverse.
Is the inverse transform. Yes, very good. OK, excellent. So that's the formula we wanted to get.
Sorry, it's not clear to me how you derive the right-hand side here.
Sorry?
It's not clear to me how you derive the right-hand side here. I can see that's what it should be. Especially it's the second term in the
How
bracket.
to derive this?
Yeah, second term in the bracket, that's not obvious.
Oh,
Or,
well, you have to start first by computing what the inverse is, right? So what's the inverse? Well, if you have a Lorentz transformation, the first thing that you do is to translate by this, and then do this, right?
okay.
Now you compose it with the next one, and you compose it with the next one. OK, very good. Those are the equations we wanted. But that's not all. Now we want to go one step further. We want to know the algebra. We want to know the Poincare algebra. So in order to get the Poincare algebra, what we do is what somebody suggested already, which is to take lambda and a to be infinitesimal again. Okay? But not in this formula. We do it in that formula. Okay? So we start from here, and we want to find the Poincare algebra. That's what we want. And in order to do that, all we do is to take lambda to be infinitesimal. We can do it, let's call it omega prime or omega tilde. It's not the same as the previous one. In fact, the previous one doesn't appear anymore. We don't have the previous transformation anymore. There is no omega anywhere here. Okay, so we could use the same omega. But in order not to be confused with the indices, in order to avoid confusions, let me put a tilde here. And we can also use an epsilon tilde, if we want, for A. Now we plug that in here, and here, and here, and expand out everything. And when you do it, this is again another exercise for you. You find the Poincaré algebra. So this is one exercise that is good. It's good to do it once in your life. So please try to do it, maybe now, or meaning today, or in the near future. But it's only something that you have to do once in your life. That's why I'm not doing it again, because it will be, more. So what you will find is that from that computation, if you compare the coefficients on both sides of the infinitesimal transformation, you will find that the j's, the commutator of the j's, with an I here, is nothing but this combination. Now you can tell why this is something that you want to do only once. Okay? That's the goal, to prove that you get something like this. Now this one is more reasonable. Okay? And of course, this is something we all know, which is that this part is 0. Okay? Very good. So now, this is what we mean by finding the algebra. First, we find infinitesimal generators. Okay? We see how the infinitesimal generators transform under the group. Now we take the group action to be also infinitesimal. And by comparing both sides, we find out all the commutation relations between all the generators of the group. Okay? So we have to find out how everybody commutes with everybody else. So this is a whole set of generators, and this is all the information we need. We could, of course, write these as structure constants. These, in fact, are the structure constants. Okay? So we could arrange them in that form if we label the generators in a particular way so that they have indices from 1 to 10. Okay? So in order to read out the structure constants, we will have to relabel them and simply call them generators from 1 to 10, and then write down what the structure constants will be from this algebra. But this is the way we want to use it, and we don't have to do anything else. Now, there is something particular here, something interesting about P, a very important difference between P's and J's. Apart from the fact that the P's commute, which, okay, is important, but what else? What else do you see? Is there something interesting about the commutator of P and J? It's given in terms of only what? Of only P's. That's right. So it's given in terms of only P's. So that means that the translation algebra, that the translation part is a subalgebra. But not only is a subalgebra, that we knew from the fact that translations were a subgroup, but it's a very special subalgebra. What kind of algebra it is? It's an invariant subalgebra, right? So the translation part is an invariant group of the Poincaré group. In terms of the algebra, it's an invariant algebra, meaning that the commutator with anything else is always within the subalgebra. Okay? So anything else means with itself or with some other generator, in this case J, closes into the same set that you had before, which is a subalgebra generated by the P's. Okay? So our Poincaré group has an abelian invariant subalgebra. That's part of the what makes the algebra interesting and also complicated. Okay? So we now want to, the next step will be what? To study representations of this algebra. Why do we want to do that? Well, first of all, I have to tell you what I mean by representations. I think I told you yesterday. Imagine that you have your Hilbert space, okay? The Hilbert space of nature, somehow. And you act with a Poincare algebra on it, okay? So what we would expect is that this Hilbert space will decompose somehow naturally into blocks that transform into themselves under the Poincare algebra, okay? What I mean by that is that your Hilbert space is a big, big object. Now we can find linear combinations of these vectors so that when we apply the Poincare generators to them, some of these blocks transform into themselves and don't talk to the other ones, okay? The whole Hilbert space is a big representation of the Poincare algebra because the algebra acts on this space, okay? But these individual blocks are somehow special. Somehow they are the unit elements of our Hilbert space. Somehow they are the atoms of our Hilbert space. Now these atoms of our Hilbert space, they have a very important name. You know what they are called? Very good. That's a mathematical name, irreducible representations. But what's the physics name of those basic atoms?
Particles.
Particles. That's what we call particles. So we are in the search for particles. So even without actually doing it formally, we have introduced a concept of irreducible, means that we have a set of objects, of a set of states, where the algebra acts on them, and it's impossible to find a linear combination so that the algebra will map a subset of them into themselves without talking to the other ones. In other words, the algebra will not be able to be represented as linear operators which are block diagonal, okay? So that's the statement that the representation is irreducible, okay? We're going to do much more tomorrow in the context of actual, of general algebras. But this is what I wanted to say. So that's what we think about when we talk about particles, okay? Now, how do we start our search for irreducible representations? So how do we start our search for particles? Well, we have to find ways of labeling these particles. Well, we have these operators, okay? They are Hermitian, so their eigenvalues are real, right? So we can start searching for interesting eigenvalues, okay? Well, we know that P0 was special. It's the Hamiltonian of the theory, okay? So if we search for all possible operators that commute with P0, somehow we get ourselves a set of operators whose eigenvalues will be conserved, right, in time. Because precisely the Hamiltonian is a generator of translations in time. So whatever we do to classify particles should be something that we can do so that it's preserved in time. We don't want something that will change in time all the time, okay? So what are the operators that commute with P0? That's why the algebra was so important.
P1, P2, P3.
Very good. P1, P2, and P3. Anybody else? Are there any J's that commute with P0?
The spatial ones?
1, 2.
The spatial ones?
Excellent, yes. J123, sorry, J23, J31, and J12. Those are the only ones that commute with P0.
That's also P0.
Excellent. Very, very good. Yeah. Very good. So that's what we're going to use. So you see, you spoiled the joke. I was planning to tell you, you're missing one that is important. OK. Do I want to keep this here? Well, you all remember this, right? Very good. So I'm going to make a choice. I'm going to label what I'm going to call one particle states by their eigenvalues under the momentum vector P. In other words, I'm going to label my states something like this, where P is their eigenvalue when I apply P to them, and sigma is any other label needed to describe the representation. OK? Well, what's convenient about this is that, of course, the P's will have to be real, and they are interpreted as the momentum of this particle, or whatever particle we are going to construct. So what's important about this is that somehow we're done with the translation part. OK? Now what we want to do is to understand what happens under a Lorentz transformation to these states. So let's understand what happens under Lorentz. Well, if we apply this transformation, here I'm assuming that the translation part is 0. So I'm just applying a Lorentz transformation on this state. What am I going to get? Any ideas? It's very natural to think that what we're going to get is some linear combination of states with eigenvalue under the momentum, which are given by some Lorentz transformation, right? Well, that's our intuition, but let's try to see that it's true. So let's find out what the eigenvalue of this new state is under this operator. That's what I want to do. The steps we're doing now is something that we can do for any algebra. In fact, soon we will do it for SU2, OK? But let's keep going here, OK? The steps we're going to do in the next half hour, I think. Let's see. Yep. This is something, yeah, I have to warn you somehow. You should pay close attention to what we're going to do, OK? Because the steps look a little bit funny sometimes, OK? But if we work together, hopefully we're going to get to the end, which is a very nice conclusion. But we have to follow every step carefully. Otherwise, we're going to get in trouble. Okay? So we want to compute the eigenvalue of this thing with respect to p mu. What can we use? Is there anything on the blackboards that is useful for that? What we need is somewhere in the blackboard. Somehow, if we were able to use this formula, we would be in business, right? That would be great if we could use this formula. Well, let's write that formula in a slightly different way. So the formula we want to use is that one over there. But let's actually write that formula for the inverse, for an inverse Lorentz transformation. Not for that lambda, but for an inverse lambda. So we're going to write it for lambda inverse. Now we get this, right? Because I'm doing it for lambda inverse. Exactly the same formula, but for lambda inverse. And I'm using that this is just the inverse. I want to do it for a Lorentz transformation without A. Okay, that doesn't change anything. That was general. So it's also true for this. Now let me put the inverse outside and this inverse inside to get. We're using the notation where if we have 0, we just don't write it. Okay? Now, what if we multiply by u of lambda on this side and on this side? That looks like something reasonable to do, right? So multiply by u of lambda, or apply u of lambda to this equation. What do we get? On this side, we get the identity. Is that clear? Let's see from this point of view. Any questions? Is this step clear? Very good. So we're just applying this formula we got here with lambda, with a Lorentz transformation, which is lambda inverse, the lambda that we're using here, the inverse of this transformation here. We're just putting the inverse out, and this inverse out, which cancels this one, and we're multiplying by u of lambda, and we get this nice formula. How can we use this formula here? Now it's exactly what we need, right? Looks spectacular. Because this is nothing but p mu u of lambda applied to p sigma, okay? But this is exactly what we have there. So we can replace it and say that this is u of lambda times lambda mu rho p rho acting on p sigma. But by construction, this is an eigenstate of the momentum operator. So we can replace p rho by the little p, okay, by their eigenvalues. So this is an operator, but acting on these states, we can replace them by these nice real numbers, little p's. So this is the same as u of lambda, lambda mu rho, little p rho, p sigma. And this is nothing but, this is a bunch of real numbers. And our operator commutes with them. We can pass the real numbers to the outside, and we get mu rho, p rho, u of lambda, p sigma. Okay? But this is the eigenvalue equation. Okay? Or the eigenvector equation for this state. So that means that this state, when you apply p mu to it, this is what you get. And therefore, the state is an state that has lambda p as the momentum label, right? So what do we conclude from here? We conclude that this state, whatever it is, must be a linear combination of all possible states that you have available with precisely momentum equal to lambda p. Okay? So that's the conclusion we get from here. We get so the conclusion is that U of lambda p sigma must be a linear combination of all possible states that you have available in your Hilbert space with momentum lambda p with some coefficients that depend on lambda and p. Okay? Now, this is the structure of these C's is what we are after. If we find that these matrices, sigma, sigma prime, these are now big matrices on our Hilbert space, we want to find a way to construct them in such a way they become block diagonal. And each block will be called a particle. Okay? Any ideas on how to do that? Well, if you ask me, that sounds complicated. So it's a good thing that people came out with a trick for doing that. And the trick is the following, is to know that whatever block diagonal pieces we're going to get, they will have some properties that will distinguish them from the others. Okay? Or, said in another way, they will have properties that will always be the same within the block. Okay? So we're after quantities that will be invariant, that will be always the same inside the same block. Okay? So we are after quantities that are Lorentz invariant. So what is a Lorentz invariant that we know? P mu, P mu. Okay? This quantity cannot change under a Lorentz transformation. So whatever block we find will have the same value of P mu, P mu. Okay? So as a first label for our irreducible representations, we can assign the value of P mu and P mu within that block. Okay? So that would be the first label we want to give to the block. Once again, the reason is that whatever this quantity is, we know that if two states have different p squares, so this is p squared, the two states cannot be in the same block, meaning they cannot be transformed one into the other by a Lorentz transformation. So those two states will have to be set, or will have to be distinguished as different particles. Okay? But this label for these blocks, or these labels for the particles, is what we call the mass of the particle. Okay? So when somebody asks you what is the mass, you can now tell them all this story and tell them that this is what you mean by a mass of a particle. Okay? Very good. What else? Do you know any other thing that is Lorentz invariant? The what?
The second Casimir operator.
Yes. In the theory of Lie algebras, this would be called a Casimir operator. Yes. Okay. There is one more, which is that if p squared is less than 0, then it turns out that the sign of p0 is Lorentz invariant. Therefore, we can also classify particles by the sign of P0. Okay? So these are the two things we have at hand, which are very easy to pinpoint. Okay, so let's see. Now, what do we do with that? Well, we know that representations will have to have a particular value of the mass and a particular value of the sign. So let's consider let's pick a particular state, a special state within the set of all possible states that will have the same p squared. Okay? So let's consider a reference vector, which we're going to call k. Okay? So k is a particular vector that has the mass, whose norm is minus the mass squared of the particular particles we're after. Okay? What's the reason for choosing a reference vector? Well, the reason is the following. We can construct any other vector in the same set of objects that have p squared equals to minus m squared by applying a Lorentz transformation to this reference vector. Okay? After all, a Lorentz transformation will not change k squared. So we know that there exists a Lorentz transformation, which I'm going to call L, because now this is the way the Lorentz group is acting on a vector. Okay? So I'm just going to call it L to distinguish it from all the other Lorentz transformations that we had. But it's just the regular 4x4 matrix that is acting on a vector to give you another vector. Okay? So don't be confused by the notation. This is just another way of denoting a 4x4 matrix that leaves our metric invariant. Okay? So this is a Lorentz transformation.
Excuse me, what's this thing before nu?
This particular Lorentz transformation is something that takes k into p. Therefore, it depends on p. Yeah, OK. Yeah, very good, very good. All right. So what do we want to do? Let's see. Well, we want to make a definition. We want to start with our state k sigma. Okay? There will be a state related to this momentum. And we want to define our state p sigma to be, we're going to define it to be u of LP, acting on our state k sigma. Okay? So that's the good thing about defining a reference vector, that we can now define everything else with respect to it by applying Lorentz transformations to it. So this is a definition of what we're going to mean by these states. Now we want to go back and try out and repeat part of that computation and see what happens. Okay? So we want to apply. I know that the whole argument looks very complicated and long, but remember, what are we after? In this whole blackboard, what do we want to get? What is the goal? We should find what? The what? We want to find these guys. That's what we're after. Okay? Let's not lose sight of what we're after. We want to find those C's. Okay? And we decided that it was too complicated to just deal with the whole structure of the algebra, of the Poincaré algebra, all at once. So the trick was to divide into pieces. And we're looking at the pieces that contain a particular value of p squared. Okay? And within those guys, we consider a reference vector and define everybody else with respect to it. So all the states in our Hilbert space with the same value of p squared will be defined with respect to this reference vector. Okay? Now we can go back and apply our formula there. Which is now given by this. And hope that something simple is going to happen soon, because otherwise we're going to be in trouble. Okay. See how much we want to do today. Okay. So let's continue. What is this? Well, these are group elements, so we know how to put them together. Just one Lorentz transformation after the other, acting on our state K. And here comes again another trick. This is trick 2. So what we want to do is to write this formula as follows. So note that LP acting on K by definition is equal to P. Right? Now lambda LP acting on K is equal to lambda P. Right? Now what if I now act with what do we want to do? Let's see. What if I now act with what I'm after is some other transformation that I can apply to this, such that I'm going to get K back. Can anybody think about a transformation that will give me K back? I want to apply something to this quantity such that I'm going to get K back. Well, I have to apply something to this so that I get K. So it will have to be, remember, if I do L of lambda P on K, I get lambda P. If I want to get K from lambda P, I simply have to apply the inverse of this. And then I get K back. Well, it looks like a nice trick. It might be useless, but it looks interesting. What do we do with this? Well, we look at our formula over there, where we have lambda P K sigma. And we're going to multiply by the identity written in an interesting form. Okay? This is the identity times this object. I haven't done anything really spectacular here. All I'm doing is multiplying by this, so that when I look at this together with this, so let me cancel this inverse with this inverse. So this is just lambda P. these guys, I'm going to put them together as lambda inverse, lambda p, lambda L of p, k sigma. Okay? But this is a combination that gives me precisely k back. Okay? So that's really at the heart of the trick. We write it as something that brings k back. Okay? Now let's consider all Lorentz transformations that keep k fixed or invariant. Somehow, these are the ones that we should be looking for. That's what these guys are. Okay? So this is clearly a subgroup of the Lorentz group. It has a name, yes?
Would you define the L restricted to be some special Lorentz transformation that will leave the sigma indices in that?
No, I didn't do that. I defined this to be true. This is the definition.
Okay.
Remember, this is a definition. Okay? I define these states to be these states. Any other questions? We're almost there. I know this is like holding your breath. We're all about to die, but we're almost at the end of the tunnel. Just bear with me 5 more minutes. So this object is something that belongs to this set of Lorentz transformations that keep k invariant. That object clearly contains the identity, trivially, right? The identity times k is equal to k. The composition of two guys that leave k invariant is also another element in the group that leaves k invariant. There is an inverse for each one. Okay? Therefore, this set forms a subgroup of the Lorentz group. In fancy mathematical terms, it's called the stabilizer of k. But I don't want to call it like that. There is a better name for that, and it's called the Little group. Of k. So all transformations, all Lorentz transformations that leave k invariant, let me call them W, mu nu. So all W's, which are Lorentz transformations, which leave k invariant, form a subgroup, and that subgroup is called the Little group of k. Therefore, this object over here is nothing but an element of the Little group, which we can label by lambda and p. All right. Can you still see that one? Yeah. All right. Yeah. So why did we do all this? Why did we went through the trouble of finding this little group and doing all this? Well, the reason is the following. If we have our state k of sigma, and we apply to it u of w, once again, we can apply our momentum operator to find out what kind of states are we going to get after we apply u of w. But what kind of states are we going to get? States with momentum what? If we apply p to this, we're going to get as eigenvalues what? K, because W is designed to leave K invariant. W will not change K. That means that this object has to be a linear combination of all possible states with the same K, different sigmas. Let me call the linear combinations sigma prime sigma that depend on W. Okay? So all this suffering was just to get rid of one thing in this formula. Not in this formula, but in this formula that we got over where? Where is the formula? It's just a formula like this that is over here. Yeah, look at this formula there. For U of lambda P, what difference do you see between that formula and that formula? That's the reason of all the suffering. What? No lambda here. No lambda here. That is really the reason for all the suffering. Now we have something that acts beautifully on these states, keeping them with the same K. Okay? Now, why is that important? Well, imagine that we do U of W1, say, U of W2 on K. Well, let's apply U of W2 first. So we get, say, something that looks like d sigma prime sigma W2 on K sigma prime. Now we're applying W1 to this. Okay? So when we apply W1 to this, we get another d sigma double prime sigma prime of W1 K sigma double prime. Okay? Now comparing this formula with the formula that you get by saying that this is also equal to U of W1 W2, okay? And applying this, which is just simply sigma sigma prime of W1 W2 on K sigma prime, right? This by definition has to look like this, and this applied to this has to look like this. Now comparing these two formulas, given that we have the same K all over the place, we can conclude that d sigma prime sigma of W1 W2 is equal to the sum over sigma prime double prime of d sigma double prime. Sorry, I want to put a double prime here. Okay? So sigma double prime is equal to the sum over sigma prime of W1 d sigma prime sigma W2. But these are only matrices now. In terms of matrices, these are matrices of some dimension. We don't know yet what the dimension is. But in terms of matrices, this is nothing but a matrix multiplication. Okay? So the D's are now matrices. And removing the lambda from here, the payoff is that we don't have to worry about K's and vectors anymore. This looks complicated. All these vectors, maybe infinite dimensional representations, something complicated. We have translated all the problem into finding matrices. This is great. So matrices that furnish a representation of the little group, so that these are representations of the little group. But matrix representations. Okay? And the job is to classify all these matrices, all the possible representations of the little group in terms of matrices acting on some vector space. And once we do that, we have the D's. And once we have the D's, we have the C's, because we can now go back and use the eraser. I could find it.
Yeah, all over there.
Yeah. Okay. And we go back to this formula and say, well, remember, the goal of everything was to find these C's. Now we write this as U of remember our definition of this guy. Of course, we're taking W here to be the special W that we had before. Okay? This is true for any W's, but we can take W to be exactly the one we had before. And then if you follow the derivation, you will find that this state is equal to this one, where we apply this to K sigma. Okay? That was the purpose of the previous computation, so we probably have it somewhere. We precisely found this formula, right? Do you remember? U acting on P was equal to this U with this special L, and this U with this funny combination. But now we know what this funny combination is. We can just use our formula over there, and it's equal to the sum over sigma prime of D sigma prime sigma of W that depends on lambda and P acting on K sigma prime. Now these are matrices of numbers, right? So we can pass this guy through them and get the following. But what is this? Remember our definition of the states, right? Remember our friend here was asking us, why didn't we have a sum over there? And the reason was that that was our definition of P sigma. It's given by that. So this combination is what? By definition, is equal to lambda P sigma prime. By definition. That's our definition of this state. Is the reference guy acted upon by U of lambda P. Now note what we succeeded in getting. Compare this formula to this formula. U of P sigma is equal to D of W times this state. So we found that the C's are equal to this guys. Yes?
In the last equation that you wrote in the last formula, it should be the thing which has the brace underneath should be U of lambda. U
yeah. Thank you.
L lambda P.
Yeah. Very good. L of lambda P. That's why you were confused. Yeah. It's this guy. All I'm doing is putting this guy here because these are numbers. So we do, by definition, we apply this to this, and by definition, we get this state. This is what we call these states. And now comparing the two formulas, we found what the C sigma prime and sigma are in terms of these. So somehow we succeeded in finding the transformations of a big group, of a complicated group, by just computing what happens to something that is called the little group, something simpler. Okay? So we have reduced the problem of computing these irreducible representations to that of computing the reducible representations of these guys. So let me just finish by giving you an example. And in the tutorial today, you will do another one. So an example. Well, I should call it case 1, because there are really only 2 cases that we should consider physically. So maybe I should call it case 1. There are only 2 cases of relevance. Is that of massive particles. Okay? And case 2, which is the one you will do in the tutorial, is a case of massless particles. Okay? In the case of massive particles, we have p squared is equal to minus m squared, where m is positive. It's non-zero. That's what is important. Now, our reference vector, we have to choose a reference vector. Well, this is what we do every day. If we have a massive particle, but if we have a vector of this form, we can use a Lorentz transformation to choose a very simple vector. We can choose any, but what would be the best choice? Excellent. And what is the subgroup of the Lorentz group that leaves K invariant? Is? Oops. The subgroup of the Lorentz group. Remember, the little group is a subgroup of the Lorentz group that leaves K invariant. Rotations, three-dimensional rotations. So the little group is rotations SO3. So all we have to do is to classify, to find all irreducible representations of SO3, which we know as an algebra is the same as SU2, because Anna told you everything there is to know about the relation between SO3 and SU2. Okay? So we know that the representations have dimensions, which are of the form 2s plus 1. Okay? And for each s, we get a different representation. Of course, this has to be an integer. So s can take only values 0, a half, 1, 3/2, and so on. Okay? Now, this number, I call it s, while most of you know it as j. And the reason is that this is what we mean by the spin of the particle. Okay? So now we can classify massive particles by giving the value of m and the value of s, where s is called the spin of the particle. Of course, we know that only for integer spins, we get a representation of SO3, really. The half integers are representations of SU2, okay? Which is known as the spin group of this thing, or the universal cover of this, but we can discuss that later. What is important is that what we know as a spin, that we talk about spin of a particle, is nothing but the label of the representation of the little group. Now you can tell your friends, now I know what a spin is. I'll tell you. Is the label of the representation, of the reducible representation under the little group of a massive particle. Okay? The next case is a case of massless particles. Do they have a spin? Not really. Massless particles don't really have spin. So the reference vector in this case, we can choose it to be 1, 0, 0, 1. And the little group, this is what you're going to work out during the tutorial, is a group of rigid motions in 2 dimensions. It's funny that a group of rigid motions, meaning rotations in 2 dimensions and translations, appears as a subgroup of the Lorentz group. But it does, and that's what you're going to show. Okay? Now, it turns out that the representations of this group are interesting. It's slightly more complicated. It's a baby version of the Lorentz group, in fact, because it has translations. It's somehow the Lorentz group in Euclidean R2. But the representations are labeled by a single label, which is called sigma. This is called the helicity of the particle. So massless particles don't have a spin. Spin refers to this SO3. They have helicity, okay? Which turns out to be the eigenvalue under the third component of the angular momentum generator. And it can only take half integer values too, but with plus or minus signs. So during the first lecture, we talked about examples of particles with helicity plus minus 1. One example was what? Massless particle was the photon, right? We talk about the photon, but really the photon is 2 particles. Yeah, I'm sorry to be telling you this, but it's true. You have been fooled all this time. We think about the photon, and there is not the photon. It's really 2 particles. We have a particle with helicity plus 1 and a particle with helicity minus 1. Okay? These are 2 completely different objects. Each one belongs to its own irreducible representation of the Poincaré group. Okay? Very good. So today in the tutorial, you will work this out, and you will also review the irreducible representations of SU2. Any questions? I apologize again because the whole thing was a little bit of a suffering to get there. But I think it was worth it. And now we know exactly what we're talking about when we talk about particles. And this is all there is to know, really. Now we can add more labels, which will be internal symmetries. Okay? But that's what we're going to do tomorrow. And then we're done. Okay? No questions?
We will need some more work to show that L exists.
That what?
L that turns to P2K exists.
That L turns, that LP, can you write on the blackboard? Maybe. Yeah, maybe we can stop here and then you can have questions.